Great. So thank you so much for the invitation, for the opportunity for me to present some work today. This is work that I promise, it really will appear. I tend to not, I don't like to give talks about things that are not out on the archive, but this one, it will be. And in any case, I do want to advertise this will be work that will appear very soon with Luis Tapolo, Susana Ventaya, and Diego Lisca. And the theme of the presentation today is something that is very fun to my heart. Basically, I want to highlight, as it was highlighted on Tuesday by two talks, that modular forms are really important in understanding black hole microstates and counting the black hole microstates. Okay, I don't think this is an audience that I have to explain why, but it is quite important. Okay, and I want to revisit this. Okay, so this is a talk basically where I'm going to obsess about one integer. Sometime that integer will be 0. And I'm going to try to understand what is the meaning of 0. Okay? But basically, I want to understand this relationship better between modular forms and black hole entropy. And to give you some context and very precisely what I'm going to be thinking about, I'm going to be revisiting results related to BPS black holes and extremo, because now we learned from Tuesday, you can have BPS black holes that are non-extremo. But I'm going to consider BPS black holes that are extremo in basically 4D and 5D engaged supergravity. And as it was very beautifully shown back in 2011, these black holes, they have an area law, so they're also going to be big, fat black holes. And they also receive a quantum correction, a logarithmic correction that goes like the logarithm of the area. Okay? I want to say, for these examples that I'm going to be talking about, there's a microscopic formula, there's a gravitational computation. Things agree. Don't worry. They still agree. I am not going to tell you that they don't agree or something bad happened. No. This is not what the message of the talk is. This is where I just obsess about numbers. And I'm going to be obsessing in particular about that number. And basically, what I want to revisit is that by matching that, what did we really learn about the microscopic description? Okay, so it's my slowness in the process of appreciating how did we advance in the microscopic description by matching those numbers? Okay, so with that said, the setup is going to be the following. So let me just review very quickly what happens on either side of the computation. Okay, so we have a gravitational computation that I'm not going to, like, this is basically the summary of this gravitational computation in very brief. So on the gravity side, you will have a black hole. For simplicity, let's just say it has electric and magnetic charges. And you will be computing a path integral for some fixed values of those electric and magnetic charges. Okay? Of course, this receives many contributions, many corrections, but roughly, if you think of it in a saddle point approximation, there will be a tree-level contribution that comes from the black hole. There will be a one-loop contribution, and here, ... means basically that you will have other higher loop contributions, you will have other non-perturbative contributions, okay? But roughly speaking, this is how we think of the organization of the gravitational path. Now, following the same conventions that Ashok had in his talk on Tuesday, I didn't want it to, so that we don't learn again what lambda is, so in the same units that he had. Basically, these computations are done in a large scaling regime for the charges, for the parameters. So I'm introducing this parameter lambda here to illustrate that I have a big fat black hole. And in this context, in this regime, is where you get basically these contributions. And this little number here comes from these one loop contributions. And they come in two fashions. There's a local contribution from massless fields, and there's a contribution of zero modes that are basically from isometries, okay? So that's what goes into giving a prediction from the gravitational perspective on what is that log. Very good. Now, on the microscopic side, what happens? So very crudely, you basically have your modular form, okay? I'm not going to give you at this stage. We'll see as we go through examples, so I'll be more careful on the modular forms that we'll have in mind. But basically, you have something, an index that counts BPS states, okay? It will be something that depends on two variables. And very similar to what Samir wrote, the coefficients here of these modular forms have an exponential growth, of course, with corrections. And for these class of forms, basically the nice way how to package this correction in terms of these discriminants and what we call the maximal polarity, which I will say more about. And the hard work, what's non-trivial, and this is something that I want to highlight, is that in order to really get things to work from the red to the blue, you do have to think carefully about what this means when you go to this side, okay? So this is a non-trivial step. And once you do that, which was done for these explicit examples, then you can look at the logarithm of this number. You will get the first term and the corrections, and this is where you establish, these two things match, okay? That's the very kind of big summary of what happens in the explicit constructions. But this is where I want to obsess, and I want to revisit this. So what I'm going to focus on is not on like, oh, let's do again the red computation. I want to do again the blue computation, okay? So I want to look again at what goes in extracting this information. What are you asking out of the modular form? How do you set up the computation, and what is the data that you learn? So there will be the first part of the talk. I'll basically talk about this asymptotic expansions of these coefficients. How do you think about them? I'll also talk about implementing holographic conditions, which go under the name of HKS. The method that I will be using is crossing kernels, and this is where maybe some of you will start shouting at me. Maybe not. I don't know. In any case, I'll tell you how we thought about like an efficient way how to get these methods. Then you might be skeptical about the method, and so we did our homework, and there's some classes of forms that are relevant for the explicit examples, and so the results that we'll show here, which are quite general, are tested against symmetric product orbifolds and exponential lifts. So they show also some nice insights into what's going on, and there's also some nice properties here that I want to highlight, although they're old, but I think they're casted now in a new light, which is going to be interesting. And then we'll go back to the explicit black holes. So I'll show you two of them. One in 4 dimensions and one in 5 dimensions, and we'll connect back to the gravitational side. Now, I put here very faintly n equal 2. I'm not going to say anything about it. You're welcome to ask me about it, but this is where I don't know what string theory is. It's not a failure of the method that I'll show you from the mathematical side, but I would love for someone to tell me what string theory is so I can feel like there's like a little dot there. It's very frustrating, and I can't. Okay, in any case, I'll stop complaining. You know what string theory is, Chiyun? Well, I was asking. I have a complaint also about one of your papers, but in any case, we'll get to it. We'll get to it.
Any attempt of the microscopic derivation, one would also have to understand whether it's describing a single center block over some.
Exactly. No, there's many moving pieces there, and that's why the n equal to, there's a lot of complications there, but you could still try to understand some of the pieces that go in, and well, let's better talk about it. We can talk about it offline, because I don't want to become the bitter person that doesn't know what string theory is. Maybe by the end of my stay here, it will be completed. But in any case, yes, there's many things that here are complicated, and that's also why it's a little bit frustrating to say things very precisely, but we'll postpone it to another time. Okay, so without any more delay, wow, time flies. Let's start talking about this asymptotic expansions of these coefficients. So I'm looking at basically weak Jacobi forms, which here I'm writing their definitions. So they're functions of two complex variables, tau and set, when the sum over n positive. And they basically have this nice modular property, where here I'm highlighting the weight and the index of the form. They also have an elliptic property. What you learn from these two properties is that the nice way how to organize the coefficients of this modular form is basically by something that is called the discriminant. Okay, so this is invariant under these elliptic properties, and then it makes you separate the states into two. So you have polar states that have negative discriminant, and non-polar states that have positive discriminant. This is what I call light. This is what I call heavy. Okay? And there will be a state that has the maximal polarity, the most polar state, that I'm basically characterizing in this way with this integer b, where b is less or equal than the index of the form. Now, for these type of forms, you would tell me, we know everything about the coefficients, so why are you giving this talk? There's something known as the Rademacher expansion. So this is an exact formula for the coefficients of any weak Jacobi form. I'm here writing it for weight equal to 0. And basically what you see from this formula, very scary, is the following. So you're trying to compute the degeneracy of a heavy state, of a nonpolar state. And it's basically controlled by the light states, by the polar ones. That's what these two terms here indicate to you. And then everything else is a known function. Okay? And the famous exponential growth here comes from this Bessel function that you have with the term c equal to 1. Done. Talk concluded. Should we go drink coffee? Okay, so this is a beautiful formula. I love it. It's great to have it, but in some sense it's too much. It's too much data. It's too micro. And in which way am I complaining about this? The reason why I'm complaining about this beautiful formula and the reason why I'm not going to use it is because when I do gravity, so when I try to connect to the gravitational path integral, this parameter t, the index, will be something that I will scale as well. This is part of this dictionary on how I relate the charges to actual parameters in the modular form. The index goes in. If you want the central charge, goes in. Okay? And if you just look at this, that part of the sum, that's not great for trying to understand how things scale if t is something that goes into the range of a summation. Okay? So I need something more coarse. So I need to do a worse job. Okay? That's what gravity is kind of asking me to do. Can you do a worse job than Rademacher? Yeah, I can. I'm not as great as him. So I can do a terrible job. And so the way that I'm going to do a terrible job is by introducing these crossing kernels. So although the form itself is described by discrete set of integers and a discrete sum, let me say, no, you know what? Let me think of this as a continuous, okay? So that I have an energy, and if you want like a charge, J, okay? To reproduce the actual form, these are delta functions. So I have to think of this in terms of distributions. But basically, in this language, yeah, what I want to have this control is basically some continuous version of my parameters. And then in the spirit of Rademacher, I'm not going to use all of the modular groups. So that's what happens when you do the Rademacher expansion. You use every single element of SL2 set. Here, I'm just going to use the S transform. So my mediocrity, you just use the S transform. And if you do that, then you can see that this distribution basically gets this integral expression where this function p here is what's called the crossing kernel. And it's again something that is fully fixed by just demanding that you had an S transform in the formula. Sorry, was there a question? No.
I'm trying to decide whether I have a question or not. Maybe I would just say, can you tell me whether you forgot the question? So if you have like this row as basically a big pile of delta functions, can you actually make like a nice expansion where you can just...
This is not convergent.
No, not convergent.
No, it's not a convergent expansion. So I'm terrible, and I know someone over there is going to be like, don't do that. So it's okay. Yes, so this is a terrible thing to do. That's why I knew that we had to do it many different ways to convince you that even if you do this terrible thing that it's not a convergent expansion, it's still kind of okay. So, yes. Okay. And also here, one thing to notice, this might look a little bit reminiscent to the Rademacher expansion, telling you that, oh, some heavy states are related to some other ones, but actually here the integrals go over everything. So you're really relating one state to every other configuration of the state. So this is also where you do a terrible job. But the thing that we're going to do, we're going to split this into a light contribution that goes into the kernel plus some corrections. But one thing that you can, if you squint and you look at things from afar, the error that you will get between the actual coefficient and this density is basically something that is going to be exponentially suppressed. So for the purposes of trying to extract this logarithmic correction, I'll be okay. But it's only for that purpose. So you do have to treat these manipulations with some control. So very good. So that's going to be the method. Now I want to incorporate gravity into this computation by meanings. I want to understand what would it take for me to get to the right regime. So when we write that this thing went like an exponential, usually what goes in is something that is universally valid. It's what you love as the Cardi formula, which usually assumes that delta is much bigger than delta naught. Delta naught and T are parameters that, from a mathematical point of view, are hold fixed, and from a gravitational point of view will mean that you're at high temperatures. Well, that's not what I want to do. But here, Tom already answered the question for, sorry. So to incorporate gravity into this, sorry, before I will say that in a moment, basically what we want to do, we want to have the capacity of having a large n limit. So we want T and this delta 0 to go to infinity if we wish. And we also want to be able to describe black holes that are at intermediate temperatures. They don't have to be necessarily at very, very, very high temperatures. So yeah, so Tom and collaborators basically answered this question to us. They said, okay, if you want to have an exponential growth at intermediate, on an intermediate regime, you have to impose this yellow box, okay? So modular forms whose light spectrum is bounded by a Hagendorn growth will allow you to apply this exponential in a much more extended regime. Great. Okay, so with those two inputs now, so what we're going to do is basically say, okay, use the crossing kernels and combine it with this sparseness condition and see how far you can get. Okay, so what can you say about the coefficients and corrections to the coefficients? And the answer is two things. So we basically have two different regimes in which we can describe not just the fact that the coefficients grow exponentially, but we can get the corrections. So there's one regime that we call universal, because basically you don't need to know anything about the light spectrum. The first correction polynomially here, logarithmically, when you take the log of D, is something that is basically just fixed by the modular invariance, but the only thing that you have left is a potential ground state degeneracy, okay? It's very tempting to put this equal to 1. I will show you explicitly why in the string theory examples that number is not 1, okay? So we need to keep it. Don't put it equal to 1. Now, there's also going to be a non-universal regime, which might look a little bit awkward at this stage, but this is a regime where delta 0 is much bigger than delta. And here you do need to know a detailed information about the light spectrum, but you still can compute the correction, and this is basically the correction. Still, you have this ground state degeneracy floating around, but now you can see here there's all sorts of information that depends on how the light states are growing, okay? Very good. And this parameter here, alpha, the power here, just to be clear, it's within this sparseness condition, but it has to be strictly less than 1 for this formula to valid, okay? To be valid. If alpha is exactly equal to 1, then this regime ceases to exist. Yes?
Can you say more about the weight K? What is that on the black hole side, and does it change this slide?
I'll tell you in one example, I will have a weight. It does change. This one, it changes it in a very simple way. It's just, I was lazy.
What is
It depends on like the number of dimensions that you're in, and it depends if you have zero modes or not. So for instance, so when I do the 4D computation, there's a weight because when you go down from ADS3 times S3 to ADS2 times S2, you get top knot modes and KK modes, and that adds to the weight, and that's why it's not a weight 0 form. In the n = 2 case, it's a weighted form, because you're not computing trace of minus 1 to the f, you're computing trace of f squared times minus 1 to the f. And then there's also a contingent part of the spectrum that you have to remove, and all of that gives you some weight into the form. So it's basically zero modes from the point of view of the CFT, that you have a 0.4 CFT, and then you have to be careful about that. In the simplest cases, so it will just be a weight zero form. So yeah. But in any case, the formulas here, there are some small adjustments that you have to put in here because you have a weight, but that's it. Okay. So let's test this against, so if you don't like crossing kernels, let's do a better job at symmetric product orbifolds and exponential lifts. And so let's go back to this Rademacher thing. And so I was whining here, like, T is big. Then it's like, so therefore let's do crossing kernels. And another thought that you could have had is like, well, just treat T as another thermodynamic variable. You want to know how it behaves in a continuous way? Add a Boltzmann factor to it and sum over it. Easy. Well, it's not super easy because that means that you need to have an understanding of what a family of Jacobi forms are, and then make sense of what it means to sum, like what are the representatives in here. But these are two examples where that's exactly what's happening. In the land of symmetric product orbifolds, in the land of exponential lifts, basically from the mathematical point of view, the mathematicians have given me a measure on how to sum over different indices that are described by an integer index, okay? And the sum goes from 0 to infinity, okay? And so this is another way how you can decide what does it mean to take the large n limit of these forms. And it's basically, it's called also third quantization in string theory. So, okay, so to give you an example of how this looks like, so usually what you do, you grab a weight zero Jacobi form that we usually call the seed. If you wanted to construct a symmetric product orbifold, basically, what you're doing is basically summing over the n in the symmetric product, and then this nice paper of Dijkgraaf, Moore, Verlinden showed you that you can write it in this nice product-like formula, okay? So that's a generating functional for something where you summed over n, okay? You can also just do an exponential lift. Here you also grab a weight zero form. The products here are very similar, but there's some differences, which I'm highlighting by these parentheses secretly. So the range of the sums, of the products are not quite the same. And then these are weighted forms, and then they do have a decomposition as sums over Jacobi forms, but here there's a weighted form K that goes in. But still, it's a sum, basically, of different indices. The nice thing about these formulas, and the reason why I'm writing them as products, is because then you can, in order to extract the formulas, and here I'm just focusing on the symmetric product, again, for simplicity. For the exponential lift, the story goes very similarly. You can basically notice, well, this is a meromorphic function. So do your favorite complex analysis, figure out where the poles are. You do have to do some deformations of that contour, and those are things that have to be careful. But basically, what I'm writing here in this formula is the result after doing the integration. So I had tau, set, and sigma as variables. So after doing a residue integral over sigma, you get this effective integral here. And this is basically the contribution from what we call the most dominant pole, where the main assumption is that the product of these two quantities is big. And so the dot here is basically me ignoring some other residues that will be exponentially suppressed contributions, okay? And there's also a contribution from the fact that you deform the contour, but also it's a tiny contribution to the D. Okay, but the nice thing about this formula is two things. So first of all, there's this prefactor that shows up here. So something that we showed back in 2019 is that this number, this function that shows up here, it's the residue from the point of view of the contour integral that you were doing. This is basically the polar states of the symmetric product when you take n going to infinity. Now, think about this a little bit. When we go through the approximation, the validity of this expression, I don't need to take n going to infinity. But it's kind of telling you that the relevant polar states for you to capture the number of this coefficient down here. So even if delta 0 is fixed, the convenient way how to organize your computations is in terms of the states that are at n equal to infinity, which is conceptually, you might not have imagined that. From the Rademacher point of view, you would have just said fix n and just write down the Rademacher expansion, right? You wouldn't have thought that it might have been convenient to call for states that were at infinite index. So that's kind of nice about how you rethink again about this formula. Now, the other thing that I want to highlight is basically this ground state degeneracy here. So that's what this number here shows up in. It's a possible combinations that distribute the seed ground state among the n factors. And so you see here there will be a scaling with n in this formula. And then also this part here, basically if you want to think of it from the 6D point of view, these are the perturbative states of the 6D supergravity on ADS 3 times S3. Okay, these are the quarter BPS excitations around empty ADS. And so when people matched back in 98, 99, Jan de Boer's papers, basically that's the generating function that shows up there. Okay, so they're the perturbative gravitational states. Okay, so I think, how am I doing on time? Super, 2 minutes. Oof, okay, tough. Okay, I'm not going to show how the rest of it is done, but just to rest assured, whatever we got in the universal regime and in the non-universal regime completely agrees. Okay, so now let's go to the black hole side of this. Okay, so we have reassurance that our estimates are good. Okay, so just to recap, so now I'm going to basically compare this side with this other side based on what I understood better at extracting the coefficients. So first favorite example, quarter BPS black holes and n equal 4, d equals to 4 on gauge supergravity. So let me think of this in terms of a dionic black hole, something that carries electric and magnetic charges. This is the relevant scaling. The area of the black hole is given by this formula here. The logarithmic corrections were computed. So the zero mode is basically -1. The local contribution, if you are in n equal to 4, so this is basically the number of multiplets in the n equal to 2 language. You put your information here for n equal to 4. It's also 1. What is 1 plus -1? 0. Let's obsess about 0. That is... Oh, sorry, there's an overall minus... Sorry, that's a... No, it is -1. Yeah, it's not 2. I have it correctly in the paper. I'm sorry. Like well spotted. No, but the answer is -1. Yeah. Phew. Okay. Okay. So let's see the microscopic derivation. So there it is, an exponential lift of the Gusa-Kuss form. That's the counting formula that you use. The map between these variables to the variables that I was using is this one. So this is a case where t is equal to b. Delta naught is minus q squared over n. N is p squared over 2. L is this. Okay, you can check very quickly. Here, I did get my factors correctly. It is 5, this thing. And so then what this tells you basically is that for this black hole, you are in the universal regime. You're in a case where delta is very similar to delta naught. And so then you use our formulas, and this little number here, basically for the exponential lift is 2. Is the number of Ramon ground states that you have. And this is why then this ratio here just gives you 0, and it matches the gravitational answer. Okay? So the meaning of 0 is you are counting the number of Ramon ground states. So when you matched the two sides of this computation, what you learn from the CFT point of view is how many Ramon ground states the theory had. That's what you learned. Okay. Now let's look at a second example, the BMPV black hole. Okay, good old 5-dimensional case. Also, if you want, turn off angular momentum, it would be the Strominger-Vafa configuration. So in this case, following Ashok's conventions of the scaling, So here now, just things will go like lambda squared, J will go like lambda cubed. This is the area of the black hole. Now you compute the logarithmic corrections. There's no local contributions because you're an odd number of dimensions. And so anything that happens to you, look, I put the minus sign there. Okay. Is basically, you just need to count zero modes. Okay, so here I split it up in this weird way because you have zero modes from the vector fields, you have zero modes from the metric, you have zero modes from the gravitinos. If I'm looking at type 2b on K3 times S1, the number of vector fields that the theory has is 27, and therefore that number is 4. Okay, but basically this is a computation that just comes from what symmetries the fields in your background have. Okay, there's no. That's the only thing that you're doing in this computation, which is still, you have to do it, but okay, that's what's going on. Let's go now to the microscopic derivation. There you have to look at the generating function for the symmetric product on K3. T is again equal to B. Delta 0, the central charge, is basically Q1 times Q5. N is P, L is J. You will get again your area matching. But you can see right now that you're not in the universal regime. You're in the non-universal regime. Okay? So the central charge is much bigger than the energy of the configuration. And in this case, then, you have to apply this formula, and I need to know information about these light states. So from these expressions, so what you will get is basically the light states will grow like a square root of delta. There will be a weight and a ground state here, which you can compute. And just to give you the basic information, so again, it's the same CFT in a sense. So again, this D is 2 with the same number as 4,4 CFT. So that's the number from ground states. This weight is the combination of these coefficients that come from the seed is -3. So this D00 is basically data of the K3, which is 20. Okay? So I'm right now out of time. So what did we learn from this? Okay, in this case, the gravity computation might have hinted to you that there wasn't much to learn because it was just zero modes. And it's like, okay, great, so what? This side, there's no zero modes. This part here, I need to know what the light part of the spectrum of the theory is. Just to impress you, the fact that these numbers matched, non-trivial. Okay? It's not controlled by symmetry. This side, it looks like it's controlled by symmetry. This side is not controlled by symmetry. Okay, I'm now the last bit. Okay, so the conclusion, just to show you those two examples, basically, we were going between these two sides. There's universality and simplicity that occurs in either of these two sides, but it's not preserved. So sometimes things are simple here, complicated here. Sometimes they're universal here, but then actually they depend on the content of the theory on the other side. So there's a conservation of difficulty in the correspondence. And the other thing that I do want to highlight here, that maybe also some of you might not know, and this is, I promise, this is the last thing that will come out of my mouth, is that, for instance, in these examples, when you compute these corrections, if you have modular forms, every single time here, these numbers that show up are always independent of the parameters. Basically, they're independent of N and L. They're just integers that come into the computation. We can talk about many examples where if you do this gravitational analysis, this number here depends on ratios of the charges. So I'll just let you to chew on that and what that might mean. In any case, now I'm done. Thank you.
Questions?
Do you have a simple way to explain why the 5D black ring doesn't contribute?
Samir. I do, but I think I just talked to him on Tuesday about this. And, so.
In n equal to 4 string theories and n equal to 8 string theories, they don't contribute. And
n equal to 2, they might, but we don't know, as you were discussing. And the reason they don't in higher theories of extended supersymmetry is because roughly there are extra fermion zero modes. That's I can explain this to you more. If you reduce it to 4 dimensions, it's like a two-centered configuration, one of which is big and one of this. If you lift so the actual gravity solutions are written in n equal to 2 theories, right? You have to lift it to n equal to 4, and then the statement is that they don't exist everywhere in the moduli space of n equal to 4, only on a subnode. So therefore, there are extra fermion zero modes. I can explain this to you.
I think I'm aware of this 4D argument. I just was more asking whether it's a direct 5D way to see it, because there's some subtlety with the uplifting, and you might worry that some zero modes.
Yeah, it's basically worrying about zero modes very carefully, but yeah.
I don't know of a direct 5D argument for this, and in fact, I have similar confusions in 5D about multi-centered black holes. It seems like in 5 dimensions, all the multi-centered black holes are also they go to the boundary of moduli space, something of the sort. I don't think this is well understood.
Have you thought about the contribution to the entropy that is independent of G Newton? I would have expected that on the microscopic side it could be computed.
Yeah, but no, I haven't thought about it, to be honest. No, I obsess about logarithms, for better or worse, when they all get over them. Yeah.
So you've checked this, I guess, example by example, but if I remember on the gravity side, there's a general formula where you just have number of this, number of that, number
yeah,
that's why can one just match
that's
function,
why I had
or?
like the n equal 2 like fainted away. Because in some sense, yes, I can match it, but it's I would like to have reasons why those are the right numbers, and that's why I'm getting frustrated. That I read different papers and different people tell me different numbers.
Because on the gravity side, it just depends on the light stuff.
Yeah.
But on the modular form side, it depends on different light stuff. Is that the?
No. Well, there's two things that go in. First, you have to tell me the mapping is super crucial, right? So we saw that, like for instance, if I was in 4 dimensions, how I would relate those charges to delta and delta naught was very different if I was in 4 dimensions versus 5 dimensions. This changes the regime. So I first have to specify what is the regime that is important. So you have to have some intuition of like, okay, this combination of charges is the central charge, and this other combination of charges is the energy of the state. So then that will tell me, you're in this scaling regime from the point of view of the modular form. So then that will tell me, okay, I'm in the universal regime or I'm in the non-universal regime. If I'm in the universal regime, then things should be super, super simple. And I think then, it's only the ground states that contribute. And so if you this will be something that I will be able to tell you, yes, this is right, this is not right. If I'm in the non-universal regime, then I need much more information about the light states. And this is also what happens in n equal 2. So in n equal 2, the central charge goes cubic with the charges. So it's the intersection of the 3 magnetic charges, and then you just have 1 electric charge. And so you're in the non-universal regime, and then I need a lot of information about the light spectrum. And this is where I read different papers and they tell me different answers to what. Okay, there is one, if you do then F more, there's one answer there that it will give you, but I wanted a more ADS3 understanding of like, so I was going up to 5 dimensions in that case to just understand like, what is the light spectrum that I need? And there's at least 3 different papers with 3 different answers. They all have the Euler number of the color, but yeah, so there's a part there with the number of hypers and vectors that they all agree with. But there's like this. In any case, okay.
I'm just trying to understand the bottom line of the talk. So there was one very interesting quantitative point that you made, that in 4 dimensions, the log correction is 0, and that's related to the number of Ramon ground states.
Yes.
Can you just explain that, what you meant by that?
Well, that if I would have not put in, so in, let me see. Let me write it, let me show it to you when it's written generally. So what I meant is that, so for the 4D case, I'm in here. Everything that you see explicitly as a function of delta and delta naught, it's just fixed, like there's nothing, it's not sensitive to the theory itself, okay? But you might have been tempted to put 1 there, just thought that there was just one ground state. Because if you're just doing a partition function, then yeah, you say, there's a unique ground state, put 1. So that's what I meant, that in order for you to get 0 from the modular form, you need to learn that there's actually a large degeneracy of Ramon ground states, and that goes like delta naught. And so then this ratio is, again, just 1. That's what I meant by learning what the number of Ramon ground states is.
Can we write a formula? If I tell you what the log correction is, can you tell me what the number of ground states is?
No. This is not fixed. It's an overall, like, fact. Like, I can't, modular invariance is not going to tell you what the number of ground states is, because you can just multiply the whole modular form by a number and it will still be a modular form. So, yeah. If you want, like, the exponential lift in some sense, kind of, no, but it's a seed theory that tell you, yeah, I don't have any way. You could have done the exponential lift of like not 2, I forgot to put the 2 there. It was 2 times phi 0, 1. If you would have done the exponential lift of just phi 0, 1, you would have gotten the wrong number. It's the same modular, but it's just like, was the elliptic genus 2 times phi 0, 1, or was it just phi 0, 1? Basically, that's and I don't have anything to fix that, from number theory at least.
Okay, let's break for coffee and thank